Good afternoon. Thank you for the kind introduction and thanks for sharing your time. Today I'm gonna talk about our work on designing and developing chemically selective microsensor array for the multi-analyte monitoring and multi-analyte discrimination application. So there are three main challenges in the chemical sensing system for the multi-analyte monitoring application. First is first is to develop the transducer which is capable of quantitative measurement with a high sensitivity. But this physical transducer is inherently non-specific to the analytes. So we need a chemical interface, also called as recognition element, which has the capability of selective interaction with analytes of interest and provides unique response for a specific analyte. And it is also well known that the high selectivity can be achieved with the combination of these chemical sensor platforms coated with different recognition layers, and then provide the series of unique responses for the multi-analyte recognition. And then finally, we need a proper analysis technique for data interpretation, which can be obtained from the array of these chemical sensors. So in our study, we used in-house fabricated quartz crystal microbalance array with a resonant frequency of 75 megahertz. This micro QCM arrays exhibits very high sensitivity even in the liquids and consists of 8 resonators in an array format. So it is highly suitable for multi-analyte sensing if each resonator is functionalized with a different ionic liquids, a different recognition layer, and generate a very unique response and patterns for the specific analytes. And then on top of it, we investigated the room temperature ionic liquid as a chemical recognizing material to achieve high selectivity, and then also to utilize its capability of tailoring the components of ions, anions, and cations of ionic liquids to provide a synthetic flexibility to make desired recognition layers. And then with the combination of these two techniques, we are able to develop the versatile chemical sensing platform which satisfies all the desirable requirements for the multi-gas sensing or monitoring, multi-analyte monitoring. So let's talk more about the room temperature ionic liquid. Room temperature ionic liquid, which is RTIL, is liquid salts with consisting of bulky and soft anions and organic cations. It has very special properties, especially for the gas sensing applications, even in the harsh environment, such as very high thermal stability, zero volatility, and rapid and reversible vapor absorption and diffusion process. But the most importantly, it has strong affinity to the chemical species, depending highly on the types of anions and cations present in the recognition layer, ionic liquids. And these are the schematics of the ionic liquid used in our study. But there are one drawback to use ionic liquid as a recognition film on QCM, which is very high viscosity of RTIL. So this high viscosity causes a very significant damping on response of the QCM. So the sensor can lose its sensitivity towards the analytes. So to address this issue and to provide a better immobilization strategy, we also investigated this special polymer template as a common platform of the recognition film on top of the QCM. There are several advantages of the use of this special polymer. First, due to the very high aromatic and complex structure of this polymer, it is able to uptake a very large amount of ion liquids with a relatively large elastic modulus. So the significant damping effect on the QCM response can be minimized. And also the use of the common platform provides very stable and uniform response as a baseline. Even it is utilized with various ionic liquids. So overall, the sensor's stability can be improved using this polymer template as a common platform. And let me skip this. And we use the microjet printing technique to functionalize each pixels of the array, QCM array, with different ionic liquids. Because the exact amount of the amount of the ion liquids actually affects the response of significantly affects the response of the QCM. So we need to precisely control the amount of the ion liquids when you functionalize on top of the resonator. And this is the schematic for the experimental setup. And the the analytes and its mixtures are premixed in the gas mixing chamber and then introduced into the detection cell later. And then the steady state response of our sensing system is observed by impedance analyzer. So overall 6 different volatile organic compounds and its mixtures is investigated to examine the developed chemical sensing system. And we use the 4 different ion liquid Doppler ionomers and functionalize it onto 4 different pixels to measure the simultaneous response of the sensor. And then again, we measure changes in both frequency and quality factor of the QCM, and the obtained set of sensor responses can be used as a patterns later for discrimination by LDA analysis. So this is this graph shows the real-time response of our sensing system upon the absorption, diffusion, and desorption of the acetonitrile on one resonator in an array. So the simultaneous absorption and diffusion response occurred within an initial few seconds. This very fast response time is highly desirable for the practical sensing application. And also, the sensor exhibits very high reversibility proven by the complete signal recovery to the baseline in like a couple of minutes for lower concentration and 10 to 15 minutes for higher concentration, which indicates there's no need of any washing process, and it can be used a long period of time without sacrificing the sensor quality. And we also studied the characteristics of ion liquid Doppler ionomers to see the effect on the sensitivity enhancement when it's functionalized differently. So we consider 2 cases. First is with different total volume of ionic liquid Doppler ionomer, and the second with the same total volume but different ratio between ion liquid and the polymer templates. And in the first case, 2 identical pixels of the resonator is functionalized with exactly the same ionic liquid ILDIs, but different total volume. So the sensitive, as you can see on the left-hand side, the total the sensitivity of the sensing system can be increased by increasing the total volume of the sensing material, which is totally makes sense because we have the more detection material on the sensor. And in other case, the four pixels is functionalized with the same total volume of the sensing material, but different ratio between polymer and ionic liquid. So when the different ratio of the is used, the sensor sensitivity the sensor demonstrates a different sensitivity towards the same analytes. 1-to-1 ratio shows the highest reactivity, but for the 1-to-4 ratio, we observe a significant loss of the linearity on the frequency response as a function of the concentration. So consequently, we can conclude with these observations that the sensitivity can be further increased with the carefully controlling the total volume of the sensing element, recognition element, or the ratio between the polymer and ionic liquid. This sensitivity spider graph shows the different affinity of these three ion liquids towards 6 volatile organic compounds. It can be seen from these graphs that the affinity of different ion liquids towards the gas molecules highly depends on the types of anion and cation present in the sensing material. And during the experiment, we observed two very interesting response of our sensing system. So according to the Sorbet equation, which is a very famous equation, we expect that the frequency is going to be decreased with addition of the gas molecules due to the absorption of mass. But the net increase of the net increase in the frequency for toluene absorption is observed during the experiment. And this can only be explained with the fact that the absorption of the toluene also causes significant decrease in the viscosity of the sensing material, so which results in the net frequency increase due to the combined influence of density and viscosity of the sensing film functionalized on the sensor. And the second interesting observation is the nonlinear quality factor shift response as a function of concentration, whereas the frequency change shows very linear dependent on the concentration. Although with these two extraordinary response of our sensing system, actually these observation gives more discriminative information which can be used later to improve the accuracy of the classification and discrimination of the multi-analytes. We'll get back to it later. So finally, we use the LDA technique, which is also one of the technique of pattern recognition. Yeah, and we use this technique to see how we can discriminate the mixtures of the VOCs. So the results here show that shows very high recognition rate for recognizing individual gases and its binary and ternary mixtures. Yeah, it's the last. Yeah. So we have achieved overall like the classification accuracy of 96% of with delta F and delta Q obtained from our chemical sensing system. But it has, it should be noted that if we only use delta F for to discriminate uh, the binary and ternary mixtures, then the accuracy goes down to 74%. So actually, delta Q gives very unique response and can be used as a yeah. Sorry. Yeah. Thank you.